You have fallen into Event Horizon with John Michael Godier.
On Event Horizon and my own channel, we spend a large portion of our focus on futurism. Indeed, futurism and all that comes with it is important to what we do as we try to understand this universe in which we live. That's why I'm excited today for us to be sponsored by Kaspersky to discuss Earth 2050 project. Our world is rapidly changing throughout these past few decades. New inventions, ideas, and technology have had a major impact on the whole of humankind. With this comes some uncertainty. Technology has become essential in our everyday lives, but some fear change, asking if the future is doomed, or could we very well be on the verge of a new era? With Earth 2050, go on a journey with noted scientist and science fiction author David Brin, as we learn more about what challenges we face to live in a world where the physical and virtual interact in new ways. With the Earth 2050 platform, you can use it as both a sci-fi encyclopedia and share your own unique opinions and predictions on what our future will bring us.
I noticed that you can switch between 2030, 2040 and the year 2050 to see on the map just what predictions are being made about certain places.
Right, Anna, you can share predictions, like them, and post your own comments on them, telling others what you think this world will be like.
View predictions from Stephen Hoffman, Martin John Rees, and from our friend Isaac Arthur.
The work of a futurist is never done, as you know by being a viewer of Event Horizon. Don't miss out on your chance to make predictions about what Earth 2050 will look like.
To learn more, follow the link in the description and see the future with your own eyes. Read predictions, leave likes and comments, see illustrations, and even predict the future yourself. In today's episode, John is joined by Dr. Klaus Pontoppidan. Dr. Pontoppidan is an astronomer at the Space Telescope Science Institute. He works on the formation of planets and the origin of our own solar system. He also works as a James Webb Space Telescope project scientist. The James Webb Space Telescope is the scientific successor to the Hubble Space Telescope and the Spitzer Space Telescope. As the largest optical infrared telescope ever launched into space, it is expected to spot the most distant galaxies in the universe, dust, and molecular gas around young stars in the process of making their own planetary systems, and not least, to characterize the atmospheres of exoplanets.
Dr. Klaus Pontoppidan, welcome to the program.
Thank you. Glad to be here. Thanks for having me.
Now, Doctor, finally, after all of the waiting, and people are going to ask me about this, of course, after all of the waiting for the James Webb Space Telescope, we're finally here. We're getting close to launch. So what are the steps now that you guys are going through to get this thing into space, and when is the launch?
Right. So we're going through the very last steps. Everything is built. There's just a few activities left on the observatory. I just saw the other day that in a press release from ESA, who is providing the launch vehicle, that they were shipping the second stage right now to Kourou in South America, from where it will be launched. That's the ESA spaceport. So there's basically the shipping left of the observatory itself and the integration on the launch vehicle and the launch. The main thing we're waiting for right now is there is one launch of the Ariane 5 rocket left before JWST in the manifest. They had just very recently, at the end of last month, they had a successful Ariane 5 launch, which they had a bit of a pause to work out some technical issues with the launch vehicle. That was successful by all accounts. So there's one more launch left, and it takes them about 2 months to turn around and set up another launch vehicle. And right now on the manifest, that's set for October 15, so you can do the math. But everything looks very good. I mean, I can't give you a date or a week for the launch, but that's roughly where it's going to be. And as we get closer, we'll know better.
Now, what are going to be the first steps once the telescope is up there and in place? you're going to have to do some testing, right? And calibrating and things like that. So what does that look like?
That's right. There's a sort of an unusually long process before we can see any science data. It takes 6 months for the telescope and the rest of the observatory to become ready to take science data. And there's a number of reasons for that. The first thing that happens after launch is that it's set directly on course to L2, which is a point in space, about 1 million miles out of Earth on the other side of the moon's orbit, which is a nice and stable point. We need to be out there because Webb is an infrared telescope, so it has to be quite cold. The mirror itself has to be about 50 Kelvin above, so above zero, minus 270 degrees Fahrenheit or more. So in order to get that cold, it can't be close to the moon, it can't be close to the Earth, it will heat it up. So it has to travel out there. It takes a few weeks. And on the way, it has to cool down to those cryogenic temperatures. And it has to be done in a fairly controlled way for various reasons. It also, another big famous part of this observatory is that it's much too large to fit inside the Ariane 5 fairing, so it's all folded up. The mirror itself consists of 18 segments, 6 of which are folded behind, like a pair of ears, to fit inside the fairing. And so those have to be deployed, so you get the full primary mirror, 6.5 meters across. And we also have to unfold a sun shield that helps to shield the science payload, the mirror itself and all the instruments from the heating light of the sun. It has 5 layers in it. Again, that gets unfolded through a complex process. One of the big time sinks in this whole process is to focus that mirror. And you can imagine that you're moving those wings out. That's a movement of several feet, right? But the mirror itself has to be focused to precision of just a few nanometers. So it's this enormous order of magnitude problem. You make this big movement, you have to make these tiny movements to shape the mirror just right. And of course, that's never been nothing like that has been attempted in space before. So it's a long and arduous process to look at reference stars and focus the mirror on them. First, you focus each of the 18 segments. And then you put all the segments together, to be able to point in the same direction until you have a final beautifully focused image of the star. And that takes a month or two to do that. And then after that, then you have to check out the 4 science instruments, which have a lot of different science modes. We can take a lot of different types of data, not just imaging, but there are many modes that are able to take spectroscopy. Depending on how you count, I think it's 16, 17, or 18 different science modes. And we have to check all of them out, make sure they work. And once all that is done, then we can go ahead and start actual science observations. So folks should, consider that it'll take about 6 months before we see anything really spectacular. And so it's just a matter of expectations.
The large sunshade to protect it from the sun seems awfully big. Now, is solar pressure an issue here? I mean, will you have to adjust for this thing acting like a solar sail?
That's an excellent question. The answer to that is yes, absolutely. The solar radiation will indeed push on this sun shield and basically turn the telescope by turning force on it. And the direction of that force depends on where the observatory is looking at any given time, right? We'll be looking all over the sky. We can't look everywhere in the sky at the same time, but over a year we'll be able to look at every point in the sky. So that force never evens out. So over time it builds up angular momentum in the observatory, and that gets picked up by reaction wheels inside the spacecraft. So they build up speed, and eventually they reach their limit, and you have to slow them down again, and that is done with a rocket burn. And so that has to be done regularly, and that's actually the limiting factor of the observatory lifetime. That and keeping it at L2, it's the amount of rocket fuel we have available. The requirement on the observatory in terms of lifetime is 5 years of science operations. We will have fuel for at least 10 years, and it looks like it depends on the launch, how successful that is, but it may be significantly more than that. But it's a very good question. Yes. Solar radiation plays a significant role.
Now, with Hubble and Hubble's lifetime, we were able to extend it because it's in low Earth orbit, and we were able to service it with human missions. With this age of SpaceX and, multiple launch systems and moving further and further out in the solar system, is there any possibility of ever servicing the James Webb?
So it's certainly not built for that. There will be a lot of technical issues doing that. So I think the short answer to that is that folks should not expect that is really an option for Webb. I think it's a very good point that for any future large flagships, I think it should be an important consideration to design them that way. But there are aspects of this, even if it were closer to the Earth than it is, aspects of the construction of this observatory that makes it hard to service. For one thing is that it's so cold. That's something that would make it very hard for an astronaut to even touch. So that's one important difference that would just make it a lot more of a challenge to service an infrared telescope than an optical telescope like Hubble.
In regards to what James Webb is going to be looking at. Now, this gets into what the original intent was, which is to study in infrared the early universe because of looking at very early galaxies, and they're redshifted. So you need to look in that area of the spectrum. What else can we do with James Webb in infrared? What is the profile of study of the universe that we can do outside of exoplanets or anything like that, but just actual true cosmology?
Yeah, no, that's an excellent question. And it is really what excites me about this observatory is that its infrared capabilities opens windows and potential projects, things that we just couldn't do in any other way. On the Earth, ground-based observatories in infrared, we're really limited. Like one of the big things we're limited by is the transmission of our atmosphere, in particular due to water vapor, but also other things like carbon dioxide absorbs light as it passes through the atmosphere. Right? That's one reason for the greenhouse effect. And it means that if you're interested in observing molecules that are really important for many things, including life, but also other things, water, methane, carbon dioxide, all this other good stuff, you have to go to space to do it. And that's a capability that Webb has. So it allows us to really much better understand this colder molecular universe. Like one area that personally work on that I find very exciting is to understand the composition of exoplanets. So you say not exoplanets themselves, but where they come from in our origins. The Earth, for example, we know that it's not straightforward to deliver these volatile elements, the molecules of water and other things that are so important for life. It's not easy to deliver those to a planet like the Earth. And the reason is that the Earth formed in a place where temperatures were too high for water to exist in the form of ice. And so they don't condense out to form an Earth-like planet. They have to be delivered later. Very well-known old issue. Likely in the Earth, it got delivered in the form of comets or maybe asteroid impacts. But there are other parts of the Earth that were delivered in similar ways. But an important one, for example, is nitrogen. Nitrogen is a very common element, but only about 1 in a million of the nitrogen atoms that were available ended up on the Earth. So there was a huge filter. You can imagine that we had 10 times the nitrogen being delivered to the Earth, we would have 10 times the atmospheric pressure, we would have a very different circumstance. So why did we get what we got? And is that really a common thing? If you form a terrestrial planet, will it look like the Earth? Will it be very different? And I think in order to understand that, you really have to look at the process of planet formation while it occurs. And that is something that Webb can do. Through its mid-infrared capabilities, it can measure the molecular composition of planet-forming disks at distances from the star where terrestrial planets form and outwards. So at about 1 astronomical unit, up to 10 astronomical units. And you can't really do that with any other facility. So I'm very excited about the prospects for being able to understand it better and really answer the question whether the Earth is a common occurrence or not. How random is the composition of planets, and linking the process of their formation to what we'll learn about exoplanets. Apart from that, I can go on. There are other things, there are other subjects that have come up only in the past few years, really, that were never imagined when the observatory was first designed. An important one of them is this phenomenon of Killanova, a completely different subject, that were discovered as part of the LIGO gravitational wave detector and other gravitational wave detectors, right? So these are colliding neutron stars. When they collide, they basically shake the universe. And in this collision, it is thought that they give rise to the formation of some very important elements, such as gold, for example, but also other elements, and they may be the source, one of the major sources in the universe of those elements. Webb will be able to, for the first time, follow up on neutron star collisions. So you imagine that one will be detected by a gravitational wave detector. We'll be able to go and look at it, and we'll measure the composition of that debris that comes out of it and really understand the origins of those elements. You couldn't do that in any other way. So there are several programs, actually quite a number of programs in Cycle 1 that aim to do just that. So I find that's fascinating. So yeah, I can go on and on. It's really, I think, you'd be hard pressed to find an area of astrophysics that an observatory, a general purpose observatory such as Webb, doesn't touch in some form or other.
Now, the idea, I have to follow this up, the idea of a kilonova producing all sorts of precious metals, that essentially is a nebula made of gold and platinum and other heavy elements. And that's actually out there, apparently, and Webb can help to characterize that.
Mm-hmm, that's right.
Now, do you anticipate that this works like a supernova remnant, where it just sort of expands out over time and metal nebulas exist?
Yeah, I mean, I think if they form other things potentially as well, it's just that you need their environment to form specifically those elements. But I don't know if that it's only that those are the only ones they form. But yeah, otherwise, I think that the idea is that it will be something like a supernova remnant, right? It expands, it cools, first it forms those elements. We know in supernova remnants there's active formation of dust, right? So it's not just you don't end up with a gas of gold. So they coalesce into solid dust grains from where they can be mixed into the general interstellar medium of the galaxy that they're in and be used for to build planetary systems somewhere down the line.
Now, is it still on the table that, say, like Earth's gold or silver or whatever is thought to be a remnant of a supernova itself? So is it possible that there are two different mechanisms in the universe for the production of heavy elements like this, both the kilonova and the supernova?
Yeah, there's probably both are potential sources. My understanding is, since it's not my area that I work in, but my understanding is that when you add it all together, it looks like kilonova, and you count how many there are of each and what you think the production rates are. That kilonova may be the dominant part for some of these elements. And I think an important answer that Webb can generate is that will actually be able to measure the production rates of these elements. So you can more definitively answer exactly that question and say, well, most of those elements are actually formed in kilonova or not. But we know very little about them right now because we don't have the sensitivity to make that determination with existing facilities.
Now, in regards to the nuts and bolts of this, so how much bigger and how much more capable relative to the Hubble Space Telescope in visible light, whereas this is infrared, but how much bigger is James Webb compared to Hubble?
Yeah, so Hubble has a primary mirror 2.4 meters in diameter, and Webb, it's not exactly round, right? It's hexagonal, but along its longest edge is 6.5 meters. So it's almost 3 times as big in diameter. And there is some overlap in wavelength coverage between Hubble and Webb. And where they overlap, the improvement in sensitivity roughly scales as the difference in area. So it's a factor of maybe up to 10 or so, something like that. Where it really makes a huge difference is once you go out really into the infrared beyond where Hubble could observe. There you're making a comparison with either a much smaller telescope, like the Spitzer Space Telescope, for example, it's almost 10 times smaller, or even ground-based telescopes, which are bigger in the infrared. But if you try to observe in the infrared from a ground-based telescope, one issue we already talked about, and that's transmission of the atmosphere. But another issue is that the Earth itself and the atmosphere of the Earth shines brightly in the infrared. At its room temperature, everything shines brightly. So it's really The comparison is that all infrared ground-based telescopes observe essentially as if it's broad daylight. So the difference you get in performance from the previous generation to Webb at infrared wavelengths is really like you imagine a species that has lived their whole life and on a day side of a planet, have never been able to experience night, and then they travel to the night side with their telescope and start observing there. And they suddenly realize that the sky is full of stars and there's a Milky Way and all that stuff. That's really the difference. So it's in areas it's a difference maybe of a factor of 1,000 in sensitivity. In some areas down to 100, something like that. So it's really transformative, and that's where you get into a regime, I think, where it becomes very difficult to predict what we're going to see. I think you'll find that a lot of astronomers, scientists, they can extrapolate an order of magnitude. Right? We've already scratched the surface of this thing, or we know if we get an order of magnitude better, we think we know what we're going to see. But when you're talking a factor of 100 or 1,000 times more sensitive or better, nobody can predict what we're going to see. This pure discovery space, and it's all unknown. I mean, I get very excited about just thinking about the things that just might pop out that we had no idea that we would find in that regime.
One question about. Actually, I have two questions, but the first one is studying very hot environments like the accretion disk of a black hole, which is something that we really haven't looked at very, very deeply yet. Is that on the table for James Webb, studying black holes like that?
Yes, I think the central accretion disk around a black hole is indeed. I mean, it's so hot that it will emit most of its light in X-rays. And you need an X-ray telescope to really understand that accretion physics in there. But there are quite a number of programs with Webb approved to look at a particular supermassive black holes, so in our own galactic center, but also in other nearby galaxies. And the reason that an observatory such as Webb is important for that is, I don't think not so much the accretion disk itself, but to understand the environment around the black hole. We know that there's a tremendous amount of star formation going on there. There's a much larger disk or torus around the black hole that is colder, will contain large clouds of molecular gas and dust. And so these galactic centers are very often obscured by these dust clouds. And this includes our own galactic center. And so it means if you try to observe them with a telescope that works in the optical and trying to understand that environment, that very extreme environment, you can't penetrate those dust clouds. You don't see it. You just feel it. So going to the infrared allows you to see through that dust and actually see what is going on in the environment. But I think really penetrate into, looking at the very, very hot X-ray accretion disk itself is probably something that's less well suited for Webb and more for an X-ray telescope.
Now, this hammers home why infrared was chosen, is that we really it's open, and a lot of people are like, well, why don't we just build a bigger optical telescope, a replacement for Hubble? But Webb is actually better than that. Now, does Webb have any visible light capabilities? Barely.
I mean, no. It goes down to 0.7 micron, and I think that is sort of very at the edge of what's formally considered the infrared. It's no longer visible by the human eye, but it's very close. So for all intents and purposes, no. But it does mean that there's some overlap with Hubble, for example. So Hubble has a little bit of infrared capability.
Now, the Holy Grail, exoplanet atmospheres, characterizing them. James Webb promises to give us our first real ability to do that. What exactly are we gonna? How does it do that?
Right. So there's a couple of ways, but the dominant one for Webb is using the transit technique, and that is using exoplanets that have an orbit that is inclined in such a way that the planet will pass either in front of its parent star, behind it, or both. And Webb will be able to look at both these instances, right? So if a planet is passing in front of a star, as light from the star filters through the planet's atmosphere, the molecules that are in that planet's atmosphere filter out certain wavelengths of that light. And it allows Webb to take a spectrum of that planet. The same thing or a similar thing happens when the planet goes behind the star. So you can imagine that if the planet is not behind the star, you get the light from both the star and the planet. But the moment the planet goes behind the star, it gets eclipsed. You lose the part of the light that's from the planet. And by taking the difference between the two, you can work out what the infrared spectrum of the emission spectrum of that planet is. And the second part is actually really important for Webb, because it provides a very important number that is very difficult to get any other way, and that's the temperature of the planet. Right? So it's not the same as measuring the chemical composition of the atmosphere, especially if you're interested in something like habitability. Knowing that the planet has a temperature of 300 Kelvin, a room temperature, would be really amazing. So it's primarily using the transit technique, and I think it's about somewhere between 15 or 20% of the time in the first year of the observatory spent using this method to characterize the atmospheres for a wide range of exoplanets with many different properties.
One particular type of exoplanet that we don't have in the star system seems to me to be on the table to study with James Webb, the hot Jupiter. Can we do and those are huge, so you can see them easier. Will we be able to get a profile of that kind of planet, a planet that we have no analog of here?
Oh yeah, no, absolutely. And there's a lot of observations of hot Jupiters planned. And I think that's actually a very good point. As you mentioned, Webb will be able to, for the first time, to really look at like the smaller planets with a rocky surface, that maybe potentially be habitable. But it's hard. It's really hard to do, right? And so that's the edge of what Webb can do, and I think that will be very exciting. But if you go to the as I say, quote unquote, easier planets, the bigger ones like the hot Jupiters, those are relatively easy to do, and that means that the data that Webb will return about their atmospheric composition will be done in exquisite detail. So much detail that it will be very, very powerful to understand how planets, what the physics of planets are, what their chemistry is, general understanding of what a typical planet looks like across a wide range of planet masses and orbits and so on. So I think that it really goes to the core of what I think Webb will do in exoplanet research, right? Where up until now, sure, we have detected thousands of planets, right? But we know very little about each one. Right? We know its orbit, and we know maybe its radius, but not very much more than that. And so we have all these questions. Like one thing would be that planets like stars in terms of classifying them. We know stars, it's a bit coarse, but you can think of stars as relatively simple objects that are characterized by mass and an age, and that gives you and a little bit their metallicity, their composition. But otherwise, it gives you its temperature, for example, and you can create models, and you can understand stars. And stars all form in much the same way through a collapse of an interstellar cloud, and so you end up with sort of the similar kind of objects. It's very, very coarsely said, right? When you look at planets, the way they form seems to me to be a much, much more stochastic process, right? Because it's not just a collapse of a single gas cloud. They form in a disk that has chemical and structural effects on it that act not only like climate, but like weather, where you have very chaotic processes that can completely change the way it looks. They will interact with other planets that are also forming at the same time, and that we think can really radically change the ultimate composition of those planets. So I would expect that once we start to really get a lot of detailed measurements of the composition of planetary atmospheres and other parameters with Webb that we don't get any other way, that we'll find that we have this incredible zoo of planets. And I worry a little bit. I mean, will we even be able to classify them? Is every planet going to be its own special snowflake, or is it is it some general things that we can learn? And so, really, for the first time with Webb, we can do that kind of comparative planetology. So I think it'll be very exciting.
That's extremely exciting, because we could finally get a profile of what planets in the universe look like. Because again, we look at our star system and it doesn't really look that much like others. It doesn't have a super Earth, it doesn't have a hot Jupiter, but it could simply be that all star systems are unique in a certain way, unique to them. And that just the panoply of possibilities for planets could be enormous. As you say, can we classify them? Although someone will figure out how to do that.
I'm sure.
Someone always finds a way to classify. But now, let me ask you this. All right. So when looking at exoplanets with the transit method, some stars are better than others. So are you going to be focusing on red dwarfs, or is it a better bet like the type K type stars? Or, what stars are you going to focus on to look via the transit method?
There's really a wide range. If we did look at sort of just the ensemble of all the different planets that folks are looking at. Remember that the program in the first year of Webb is really created in a very organic way, where about a third of the time is awarded to what we call guaranteed time observations, awarded to people who contributed to building the instruments and so on. But 2/3 is just available to anybody in the community to propose for, and it gets selected through peer review. And so you end up with a lot of smaller programs where individual teams decide what they think is best, right? And so it's very, very interesting to look at, what is the ensemble of objects that are going to be looked at. And it turns out it's a very flat distribution. So we have anything here, but from planets around M dwarfs to planets around solar mass stars to planets around more massive stars. If you look at the distribution in planet radius and expected equilibrium temperature of the planet, again, it's also, they run the gamut from a couple of hundred Kelvin to extremely hot Jupiters, 1500 Kelvin equilibrium temperatures. So it's we're happy to see that, right? I mean, it's not something we enforce. We're happy to see that already in the first year. I think we'll get a very good sample of all, most of the things that could potentially happen, and then you flesh it out from there.
Now, do you build in the possibility for transient events into the schedule for JWST, meaning that, say you're scheduled to do an observation for some science group, and all of a sudden we pick up some neutrinos and there's a supernova about to happen. Can you just drop everything and turn the telescope to something like that?
Yeah, no, excellent question. There are basically two ways of doing this. There are transient events that you can sort of predict, like, for example, supernova go off all the time. So you can ask for what's called a target of opportunity program. So that's just as part of the regular proposal process. And we have a bunch of those. The Killanova observations, for example, is an example of that. We think we're going to detect a Killanova. And so when one goes off, the team that got that time can say, we're going to go ahead and trigger our observation, and please go and observe it. Then there are different levels of how quickly they need to move the telescope. If it's more than a few days, then it's not a big deal. But if it's less than that, then it will disrupt the schedule and becomes more expensive in terms of telescope, what we can think of as telescope resources. The other way of doing that is that the director of Space Telescope Science Institute, which hosts the called the Science and Operations Center for Webb and for Hubble too, and I mean that's my employer, has some time available that is given to him in his role as director, and so he can award what's called the director's discretionary time. So there typically there's a process for somebody to say, this thing just happened and we had not predicted that. Can we please go and observe it? And you can put in a quick proposal, and we can go ahead and get that observed. So yeah, so there's definitely flexibility for that if there's something that scientifically warrants doing that.
Now, another type of transient event that's been in the news lately is the idea, this isn't as an urgent as like a supernova or something like that, interstellar objects. Now, when we get certain land-based telescopes like the Vera Rubin Observatory going, we're probably going to see a lot of these. Is that on the agenda, looking at those on the agenda for James Webb, and what could we do? I mean, had we seen Oumuamua earlier and we had the telescope in orbit at the time, hypothetically, say, could we have done a better job at characterizing it and answered more questions than what we were able to do just with what we have?
Yes, absolutely. I love those. I mean, interstellar objects are fantastic. I love them. I can't wait. And exactly as you say, with the Rubin telescope, we think that we're going to pick up, one a year or maybe more, who knows? Which is, I think, is a revolution from when I started out, when there was just a question of how many of those were actually around, and it turns out that there are a lot and enough that we should see them with some regularity. there is a target of opportunity program in cycle 1 that if one comes through and it's not behind the sun or something like that, that we can go and observe it with Webb. And there are multiple ways that you can get a much better understanding of such an object with Webb. Like, for one is when you're observing small objects in the solar system like asteroids or other things, and you're doing this in visible light or near infrared wavelengths, you're basically seeing reflected light from the sun. And as we know, the reflected light can look very differently as the object is rotating around its own axis, right? So they all rotate, with a few hours or something like that. If there's a big crater on one side, or there can be color differences. So people have used, and this is the case with Oumuamua as well, right? People have used the changes in the light curve as it rotates to try and estimate its shape, but it's very dangerous because of the potential presence of craters that can be shattered and other things that are not directly related to whether it's really elongated or something. When you look at a small object like in the at the longer wavelengths, the longest wavelengths that Webb can do in the mid-infrared, at some point you start to be able to pick up the self-infrared emission from the object just because it has a temperature. And that is a much more unbiased measure of its size and shape as it orbits. So you can put those two together and then you can get a much better solution for what kind of shape it has. So that's one aspect of it. And another important one, of course, is composition. Just using the same molecular bands that we use for exoplanets, that we use for protoplanetary disks, and we use for other solar system objects, Webb would be able to measure something like Oumuamua, even potentially before it gets close enough to the sun to present any kind of cometary activity where it outgasses stuff. Even just from its surface, frozen stuff on its surface, you'll be able to measure the composition of that. And then, of course, if it does get close enough and things start to come off as a gas, then you can observe that as well and measure its complement of water and potentially methane and other such things. So absolutely, I think that will be done, and I'm super excited about getting that result, to get this piece from another solar system in situ almost, and be able to measure its composition and compare that to our own local comets. I think would be very exciting.
It's going to be interesting either way, because if it's sort of like with Borisov, it could either be very, very similar, or it could be different in a very puzzling way. I mean, some people have hypothesized about the phosphorus problem in the galaxy, that maybe some areas don't have as much phosphorus. Can we answer questions like that, or are we limited on what we can measure about the chemistry of one of these things?
Yeah, absolutely. I'm also kind of curious about, so those objects, of course, are potentially incredibly ancient, have traveled through the galaxy. Who knows what kind of environments they have seen. Their surfaces will get processed by energetic radiation, depending on what they have seen over time. So they may also contain some history of the galaxy and within their chemistry. It gets more complicated, but I think once we get compositions, there'll be a lot of questions raised. But that's why we're here. That's why it's exciting work.
Well, that's one of the things about Oumuamua. I mean, what did it go through that might have caused it to behave strangely as it did? For example, if it formed some kind of a crust or something like that, and that's why we didn't see outgassing, but there was outgassing, because of the acceleration and all these things, could simply be due to factors we don't yet know about what happens to objects in the interstellar medium.
Exactly, yeah. Another question I've always had is that now we starting to get an understanding for how many there are of these sort of fossilized comets just floating between the stars. That this is probably a net sink of water, for example, or other volatiles in the universe, because they have incredibly long lifetimes. So you imagine the galaxy is going through multiple stages of star formation. Every time you form a star, you form a protoplanetary disk around it that forms planets, and then the disk probably turns out to eject perhaps most of it by some margin, most of its material in the form of these planetesimals just beyond the system itself, and they never go back into the cycle. Right? They're never used again to create new stars. They just sit there inert, and you lose that oxygen or that carbon. And now we can actually get an idea of what that number is. How much of that material is actually lost, and maybe most of the water in the universe is actually in the form of Oumuamuas.
Studying the outer solar system, what can we do with JWST as far as studying worlds that are not so easy to study, like Uranus and Neptune?
Yeah, so all planets from Mars and outwards and their moon systems are scheduled for observation, and typically for spectroscopic observation. And of course, we're looking at outgassing from potential water worlds. The obvious ones are Enceladus and Europa, but there's also Triton, for example. I'm talking about the ice giants. And then there's a large program, so not related to the planets, but to trans-Neptunian objects, because again, this fantastic sensitivity we get for spectroscopy in the infrared allows us to measure the composition of large numbers of trans-Neptunian objects, Plutos, without having to send a probe there. So right now we only have a few measurements like that from New Horizons, for example, but we'll be able to do hundreds with Webb, and again get this kind of populational understanding of what this fossilized record of our own early solar system looks like.
Now, that brings us back to protoplanetary disks, because those obviously emit in infrared. So basically, the Webb is a multi-role telescope. In other words, it's designed to be able to do everything Hubble did, but in infrared instead of visible light. So can people expect the same sort of amazing imagery that Hubble produced, or could it even do better?
Yeah, no, good question. This is something that I'm working with as well. Obviously, we want to try and produce some imagery that is evocative of the Hubble success and the sort of the transformative role that played in the public's interest in science and in science education, just by virtue of its fantastic imagery. And so the short answer is yes, we will get the same quality of images from Webb. In fact, the fields of view are a bit bigger or have more pixels, so more megapixels in the images. But of course, there will be different ways that we can speculate about and we can simulate. But I think we're not really going to have a proper understanding of what it will look like until we see the data. And it's different because it's different wavelengths, it's different tracers. Galaxies will look different. So what you see with Hubble, for example, let's say you're looking at an image of a galaxy obtained with Hubble. You see the stars, and you see dark lanes of dust crisscrossing the galaxy. With Webb, as you go to longer infrared wavelengths, well, first thing you're going to see is that dust just disappears in the near infrared, and you just get the stars. And I think that's going to look a little less colorful. But then once you go really beyond the Hubble range and into the mid-infrared, the galaxy switches around. You see these dark dust lanes suddenly in emission. They light up like fire, and it becomes the brightest part of the galaxy. And we've seen this before, of course, with other infrared telescopes, but never in very high resolution. So now we're going to get these very high resolution images of these fiery dust lanes across the galaxy. Webb has many imaging filters, which means we can create images that show colors with a great amount of detail. So we know all this will happen, but we haven't figured out yet, which combinations of colors will give the most detail. Not necessarily how to tell the story of those colors, right? Because these are not visible colors anymore. They will be colors that no human can see. They're real colors, but colors that you can't see with your eye.
Colors you can't see with your eye. There's something poetic about that. Very interesting that there is a whole spectrum, actually many spectrums, that we just can't see. Now, another nuts and bolts question is, okay, so you're looking at infrared. What difference is there between a telescope mirror for infrared observation versus an optical one? What do you coat that thing with?
So yeah, no, you would not be able to take Hubble's mirror and put it on an infrared telescope like Webb and get a very good result, because you need the mirror surface to be reflective at infrared wavelengths. And that's an important reason that the Webb mirror is covered in gold, about an ounce of gold on it, spread out very thinly. And that's a reason that it has that golden, gold has this golden color. That's because it's very reflective once you get to red or golden colors and beyond. So it's highly reflective in the infrared. That's why the mirror is covered in gold. Another big difference with Webb is not really related to it. Well, it's partly related to it being an infrared telescope. The backplane of the mirror, the part that's not the gold, is made of beryllium, which actually has two advantages. One is, again, telescope has to be extremely cold. And so if you take a typical optical telescope and you cool that down to the cryogenic temperature of Webb, it would just crack. It wouldn't behave well at such extreme temperatures. So you need something like beryllium. It has very, very nice behavior as you cool it down. And so that allows us to actually have such a cold mirror. And the other part of it is that it's incredibly lightweight. And so we needed that to launch the observatory on an Ariane 5 and send it out to L2. So the total weight of Webb, not many people realize this, it's only a bit more than half that of Hubble. And it weighs significantly less than Hubble. Yet the mirror is almost 3 times bigger. And a big part of that is that it's made out of this very lightweight material.
Now, how thick is the mirror, or mirrors rather?
The beryllium, the gold surface itself is like, it's an ounce of gold that's covering it, so that's extremely thin. But the beryllium part is, I have to look up the exact number, but I think it's maybe 10 inches or something like that.
What exactly are the temperatures involved here? How low is it going to get?
But so the mirror itself is about 45 to 50 Kelvin. And let me see, in Fahrenheit, it's almost minus 400 degrees Fahrenheit. That's a mirror itself. The sun side of the sun shield is hot because again, it gets constantly heated by the sun. And so the 5 layers have to transition the observatories from significantly more than room temperature down to these minus 400 degrees Fahrenheit. The instruments are yet colder than that. In particular, one of the instruments, the one that's called a mid-infrared instrument, MIRI. So that's actually only 6 Kelvin. It's cooled down to 6 Kelvin. That has to be actively cooled by a cooler that essentially works like a refrigerator. So it pumps and compresses a gas like a refrigerator does to keep that instrument cool.
In regards to the optics, here on Earth, we go through all sorts of trouble with adaptive optics to compensate for the atmosphere. Obviously, the James Webb doesn't have this, but is there any need for any adaptive optics technology?
Yeah, no, absolutely. So it doesn't have adaptive optics. I guess the distinction is it has active optics, which means it is not changing the shape of the mirror while observing a science object. But the shape of the mirror segments can be changed and will be changed regularly, or refined or updated regularly. And so a big part of the reason for that is the deployment of the segmented mirror. Right? So as I mentioned earlier, that you have to unfold this whole mirror from a stowed configuration, and so it becomes really critical that you can have actuators behind each mirror segment, and you can twist the mirror so it gets just exactly the right shape. And there's another reason we know we're never going to have the Hubble problem, because we can change the shape of the mirror. We also think that there's going to be some thermal forcing on the mirror. It's like we're not going to be able to keep the temperature exactly constant as we go through our science operations. So the quality of the imaging of the mirror will drift over time. And with some regularity, maybe once every 2 weeks or something like that, we have to go back and refocus the mirror using the actuators in the back of the mirror. So that's an important activity for the observatory.
The close-by exoplanets, Proxima b and the Traapist 1 system, these really interesting systems around very, very close stars. What can we do there? I mean, can we actually directly image anything there, maybe?
Yeah, that's another good question. So the MIRI and NIRCam instruments on Webb are equipped with coronagraphs that help to suppress the light of a very bright star to look for faint things next to it. And those modes will indeed be used to try and image exoplanets. There is a program for example, to look at our closest neighbor, the Alpha Centauri Proxima Centauri system, to look for additional planets in that system using those coronagraphs. That would be very exciting if you find more there, for obvious reasons. And for MIRI, for example, I think there will be significant efforts to image young planets as well, those that are still hot, although they are fairly warm, say, even though they are orbiting at quite large distances from the star, much larger distances than something like the Earth or even any solar system planet, 100 AU or more. When they're young, they're warm enough that they will shine brightly in the infrared. We'll be able to pick them up with MIRI. So I think that's another important area, detecting planets, young planets directly in direct imaging.
I seem to remember there was a paper some years ago about an infrared flash seen in a protoplanetary disk that seemed to be a planetary impact, something similar perhaps to what Earth went through with Theia. So that's another type of transient that could be explored with James Webb, right?
Yeah, no, absolutely. I think Webb is not it's not a survey telescope, so I think it'll be hard for it to pick up, to detect such a flash, because we won't be able to sit and stare at one object for a long period of time. But this is where complementarity and synergy with other observatories come into play. So if another observatory detects something like that, certainly go and follow it up and understanding it better. So that's a good point.
Now, my last question for you today is this. NASA has recently started putting some thought and interest into technosignatures, the possibility of seeing some evidence, or biosignatures, some evidence of alien life, simple or complex, and see if we can detect that and what ways we could detect that. What would James Webb be able to offer there? Is it really just not its role, or would it function as something like, okay, you see something in infrared, maybe it's a Dyson sphere, we should take a look. So is that on the agenda, or is SETI just sort of not quite what it was designed for?
Yeah, Dyson spheres, I think not so much, but certainly biosignatures, if that's what you mean, in the atmospheres of exoplanets. Biosignatures being the combination of multiple molecules in the atmosphere that couldn't exist at the same time in chemical equilibrium, such as oxygen and methane at the same time. So that we'll certainly look for, and I think actually we have a real shot at detecting biosignatures if we're lucky. With some effort, and it'll be difficult. And if we can't quite get to that, right? Think of this as this is an endeavor, right? That is generational. Where when Webb was first planned, nobody thought we'd be able to do this. I think we'd be able to essentially develop something like the transit technique, the methods. We'll be able to walk right up to that door in terms of biosignatures in atmospheres. We may not be able to walk quite through that door yet, but we'll be able to take this huge leap toward it, and the next mission would be able to walk through the door, and it will inform what that mission ought to look like. And I think it will drive future missions, even if it gets done by the generation that comes after us, to something that's very large, which is, I think, what you need to make that discovery. I think you can't do it with something small. I think you have to have something that's very large, and can't do it any other way. And that's an important point to make. Webb is $10 billion. If you took the $10 billion and you cut it out into 10 smaller $1 billion missions, you'd never be able to do the science that Webb does. And that's true for future observatories as well. Putting in the money to build this big thing, that is what you need to answer the biggest questions.
When Hubble first came on the scene, obviously it had, as you earlier mentioned, the optical problem that it had that we were able to correct. But once we did, the science and the pictures were absolutely stunning and amazing. And it seems to me that the JWST has the potential to outdo that and be even better, and really fire the imagination again of the public with amazing photography. So I wish you good luck, Klaus. I hope you'll come back as the mission proceeds, and good luck.
Thank you so much for having me. It's been a blast.
Thanks for listening. I am futurist and science fiction author.
Wrong channel.
No, it's not. Thanks for listening. I am futurist and science fiction author John Michael Godier, currently hosting Event Horizon and wondering where Anna actually came from. One day I had a tablet computer, the next I had a boss. Very disturbing, and be sure...
And that's enough of that.
YouTuber forever! Like, subscribe, and hit the bell!
Sell out.
What?